Welcome back. Right, so in the previous video we were speaking about finding the equation of a tangent line to a curve, right? And we ended with this general formula right here, right? That y minus f of a is equals to f prime of a into x minus a, right? And all that this formula was talking about is that when you want to find the equation of a tangent line, right, you need a point of contact, which is this given point x is equals to a, right? That point will always have a corresponding y value, f of a, right? And the important thing to remember was the fact that the gradient, right, at that given point x is equals to a on the curve y is equals to f of x is equals to the gradient of the tangent line, right, at that point x is equals to a, right? And that's represented by f prime of a, right? But more often than not, for this specific section, examiners are not actually going to ask you to find the equation of the tangent line, right? But rather what they like to do is to use this piece of information right here, right? The fact that the gradient of the tangent line, right, is equals to the derivative at that point. Right, so now today I just want to show you another example of a question that falls into the section, right, an equation of a tangent to a curve, right, but rather they're not asking you to find the equation of the tangent to the curve. So that is going to be highlighted in question number 9a, right, and this is taken from the IEB paper. This is a supplementary paper from 2015, sorry. Right. So this question says that the gradient of a tangent to the curve defined by y is equals to k times x cubed plus l times x squared at the point 1, 5 is 12, right? And you're asked to evaluate the value of k and l, right? And this is more of the typical questions that you're going to see, right? And all that these questions are just secretly simultaneous equations, right? And whenever examiners can test your ability to do more than one thing at the same time, they will do it. Okay, so this is those type of questions where you are integrating knowledge from different areas of maths, right? So namely simultaneous equations, and we're going to have to integrate the knowledge that we have now gained from calculus, right? When you analyze the equation of your given curve, right, we are going to speak more about these curves in future videos, right? This curve, right, is what is called a cubic function, right? And this is a polynomial in the third degree, right? And you will hear me say that sometimes. So when I talk about a polynomial in the third degree, right, I'm talking about a cubic function, right? And the only reason why they call it a polynomial in the third degree is because its leading term has an exponent of 3, right? When you talk about a polynomial of the second degree, you've already seen that, right? That is your quadratic function, and a polynomial of the first degree is your straight line function, right? So this question, right, the way that you should actually approach it is to realize that it is two questions in one, right? The first question stops right here, right, when it talks about the curve defined by this equation at this point, right? So when they give you that information, you should realize that you have been given a value a, right? You've been given an f of a, right? Okay, so it means that if you had to call this function y f of x, right, what they've basically given you is the fact that f of 1 is equals to 5, right? So if you say let y equal f of x, right, then f of 1, right, is equals to 5, right? And what does f of 1 mean? F of 1 means everywhere where you see an x, right, substitute the value 1, right? So our equation is defined by k times x, which is going to be substituted with 1 cubed, right, plus l, right, times x, which is going to be substituted with 1 squared, right? This is equals to 5, right? 1 cubed and 1 squared are both 1, so therefore this is just k plus l is equals to 5, right? And lo and behold, see what you've done. You have now created an equation number 1 for yourself, right? Then the second part of this question lies in this information. The gradient of the tangent is 12, right? And what should be ringing in your head is the fact that the gradient of the tangent line, right, is given by the derivative function, right? So what they've given you here is f prime of a, right? They've given you the value of your derivative function, right? So this means that you need your derivative function, okay? So you can say f prime of x, right, it's going to be equals to, this is just simply the power rule, right? So you have 3k times x squared plus 2l times x, right? So this is your derivative function, right? This is in general form, right? But you've been given f prime, right, of 1, right, at a specific x is equals to a value, right? Okay, this means that into this f prime formula we need to substitute 1, right? So we're going to have 3k times 1 squared plus 2l times 1, right? But f of 1 we are told is equals to 12, right? So 12 is equals to 3k times 1 plus 2l, right? And now you've set up a second equation for yourself. Okay, so now you're done with basically analyzing and extracting the information out of the question, right? So now we're just left to solve a simultaneous equation, right? You can actually then go to equation 1 and solve it for one of the variables k or l, right? So let's solve it for l, right? So l is equals to 5 minus k, right? You can call this equation number 3. Right? Then it's just a matter of simply saying substitute equation 3 into equation 2. Right? So this will give us 12 is equals to 3 times k, right? Plus 2 times l, but l is going to be substituted with 5 minus k. Right? Then we're going to have 12 is equals to 3k plus 10 minus 2k, right? So we have 12 is equals to, well, 3k minus 2k is just going to be a k, right? Plus 10, right? Then 12 minus 10, right, is going to be 2. Okay, so that gives us our value of k, right? We can then say sub k is equals to 2 into equation number 3, right? And there's our equation number 3 over here, right? So we have l is equals to 5 minus k, which is 2, right? So l is equals to 3. Okay, so it means that your initial cubic function is actually defined by the equation y is equals to 2x cubed plus 3x squared, right? So that is just your equation of your cubic function, right? So notice how in a very subtle way they could have also, instead of saying calculate the value of k and l, if they wanted to, they could have said find the equation of the cubic function, right? Or find the equation of a curve, right? That is the same thing as saying calculate the value of k and l, right? So that's basically it for the section that looks at the equation of a tangent to a curve, right? Be aware of the fact that they're most probably not going to ask you directly to find the equation of a tangent, right? But if they do, you know how to approach that. Okay. What I'm going to do is I'm going to use question 9b, right, to lead into our next topic. And our next topic is the second derivative, right? So we're going to come back to this question in just a few, right? Let's just go into a new page and talk about the second derivative. So up until this point, we've been focusing a lot of our energy in the first derivative function, right? And we said that the first derivative function is the function that helps us, right, to calculate the gradient of a tangent line at any given point on our curve, right? However, there is also what is called higher order derivatives, okay? And in grade 12, we are only going to be concerned with the second derivative, right? Okay. Which I've already shown you that we can represent the second derivative with the following notations, right? So when we talk about the second derivative, we're going to use the notation y double prime, right? F double prime of x d squared y by dx squared. Okay, just notice where the squareds are in this specific notation, right? You can also talk about d squared by dx squared of a function f of x, right? Or you can simply talk about dx squared of a function y. Okay, so these are all the notations, the different notations that you can use to represent the second derivative, right? So why do we need the second derivative? Like, why do we need to complicate things even further, right? Because we can. I'm just joking. So the second derivative, right, helps us to locate, right, on our cubic function, right, points that we call points of inflection. Okay, and I've already shown you a general sketch of our cubic function, right? So this is y is equals to ax cubed plus bx squared plus cx plus d. Right? That's the general form of our cubic function, right? Our cubic function is defined by 6 points, right? It's going to have at most, right, 3 roots, right? And by roots, I'm talking about these x-intercepts, right? Okay, so because it's a third degree polynomial, it can only have at most 3 roots, right, or x-intercepts, right? Then something else that defines our cubic function is these points over here, right, where the gradient to the tangent line, right, is equals to 0, right? So these points where we have horizontal tangent lines, okay, we call these points stationary points. Right? And these occur when dy by dx, right, which is your first derivative, is equals to 0, right? But the second derivative, right, is going to help us to locate another special point, right, namely this point right here. Okay, and this point we call the point of inflection. Right, so the second derivative function, right, is going to help us to locate this x value, right, where that point of inflection occurs, right? So a point of inflection, right, is basically where your cubic function is changing from either being concave up to being concave down, or the other way around. It can be changing from being concave down to being concave up, right? Okay, so the way that we are going to locate this x value at our point of inflection is that we're going to work with d squared y by dx squared, right, is equals to 0, right? So in other words, what we're saying is to find your stationary point, we use the first derivative equals to 0, or we set, right, the first derivative equal to 0, right? And in order to find our point of inflection, we set the second derivative equal to 0, right? Okay, so how do we actually compute this second derivative? Well, luckily for us, we don't need to learn any new rules, right? When we want the equation of our second derivative function, it's just a matter of differentiating our first derivative function again, right? So you're going to go through the process of differentiating twice, right? So you're going to start off with some function f of x, right? To get to the first derivative, you take f prime of x, right? To get to the second derivative, you're going to take f prime of f prime. Okay, so now let's compute just a few equations, right, of the second derivative function, right? Right, so we now have on screen, right, 5 different equations, right? And for each of these equations, we're going to find the equation of the second derivative function, right? So let's start off with example number 1, right? So in example number 1, we have a quadratic, right? And a quadratic, right, is a polynomial of the second degree, right? So this does not have a point of inflection. So there is no point of inflection, right, with our parabola, okay? So it means that our second derivative function is just going to be a constant, right? And what that is representing is the constant gradient of our linear graph, right? So remember that, okay, let's go through it. So g prime of x, right, is going to be equals to nx, right? G double prime of x is just going to be equals to 10, right? So this just means that all along your first derivative function, okay, the gradient of all the tangent lines is just a constant gradient of 10, right? So for us in example number 1, the second derivative function does not speak in any way, right, to a point of inflection, right? We only talk about points of inflection, right, when we talk about this function over here, the cubic function. Right. So let's go to example 2, right? So in example 2, we actually do have a cubic function, right? We have 8x cubed minus 7x, right? So we want to find the equation of the second derivative function, right? So the first thing is to take the first derivative, so dy by dx, right? That's going to be equals to 8 times 3, that's 24, times x squared minus 7, right? So that will be your first derivative, okay? To get the second derivative, d squared y by dx squared, okay? That means take the derivative of the first derivative, so we do the power rule again, right? So we have 24 times 2, that is 48, right, x, and the constant function falls away, right? So this is the equation that describes our second derivative function, right? And when we set this equation, okay, equal to 0, we're going to find the x coordinates at our point of inflection, okay? Moving on, number 3, right? We've got k of x is equals to a product of two functions, right? So now remember that before we can even take the derivative, we have to manipulate this out. Okay, so we're going to have k of x is equals to x cubed, right, minus x squared plus x minus 1. Okay, again, this is a cubic function, right? So we are able to now take the first derivative. Okay, so k prime of x, this is equals to 3x squared minus 2x plus 1. Okay, once we have our first derivative, we can take the second derivative. Okay, so k double prime of x, this is equals to 6x minus 2. Okay. Right. Example number 4, we have p of x is equals to minus 10 divided by x squared. Right. We know that when we have a variable in our denominator like that, the first thing we do is we take it up. Right. So we move this x squared to the numerator. In doing so, is going to change its exponent to a negative exponent. Right. The reason why we do this is so that we can apply the power rule. Okay. So applying the power rule means that we are taking p prime of x, right? That's going to be equals to minus 10 times minus 2 is going to be 20, right? Times x to the minus 3, right? For now, I'm not going to take this into the denominator, right? I'm going to leave it where it is because I need to take p double prime of x, right? So p double prime of x is 20 times minus 3, right, which is minus 60, right, times x to the exponent minus 4. Okay, so if you really wanted to now, you could write this as 20 divided by x cubed, and you can write this minus 60 divided by x to the exponent 4. Okay, right, last example. We have to find d squared by dx squared of this function 6 times the cube root of x squared. Okay, right, so when we do this, we can start by saying let, right, f of x equal 6 cube root of x squared. Right, so once we have that, we are able to manipulate it on the outside. So we have 6 times x to the exponent 2 over 3, right? And because we need to take the derivative and they've represented it with d squared by dx squared, I'm going to say f of x equal to y, right? That's going to allow me to say dy by dx, right, is equal to 6 times 2 over 3. Right, times x to the exponent 2 over 3 minus 1, right? So dy by dx is going to be 4 times x to the exponent minus 1/3. Okay. Now we're going to leave it like that and go into d squared y by dx squared. So this is 4 times minus 1/3, right, times x to the minus 1/3 minus 1. Okay, so our second derivative function is going to be equals to minus 4 over 3, right, times x to the exponent minus 4 over 3. And if you really wanted to, you could clean this up and write it as minus, right, 4 divided by 3, okay, times the cube root of x to the 4th power. Okay. Right, so this is how we compute, right, our second derivative function, right? And the applications of our second derivative function is to help us to locate the x value at our point of inflection, right? There is also one other application of the second derivative function, and it's what's going to be called the second derivative test, right? So with your cubic function, as you can see, you can have at most 2 stationary points, right? So now these stationary points can either be what we call a local max, right? So a local max, right? And it's called a local maximum, right? Because obviously the graph, right, has a higher y value than this one at some point in infinity, right? So if you can imagine this goes on and on and on and on, right? So there is some y value that the graph attains that's much bigger than this y value here at the stationary point. Okay, so we call it a local maximum, right? So in this area, this is the biggest y value that we attain, and it really is the only maximum that we are going to be concerned with in grade 12, right? And it's what we're going to use when we go into the applications of calculus, right? Okay, so at this local maximum, right, you have some x value, let's call it x1, right? Okay, if you want to test or verify, in fact, that this is a local maximum, right, we use the second derivative test. And the second derivative test says that first of all, you must have a stationary point at that x is equals to 1, right? So dy by dx must equal 0 at that x value, right? And if that is the case, right, in other words, you have a stationary point, right? If you want to know whether that stationary point is a local maximum or a local minimum, like what this one is, right? For a local maximum, right, d squared y by dx squared, right? So the second derivative, right, is less than 0, right? And the way that I remember this is basically these two halves, right, are sort of like mini parabolas, right? And remember with our parabolas, we said that if it's facing down like this, then it's a sad parabola, right? So if you are sad, you are negative. Okay, so the second derivative, right, is negative, right, at a local max, right? At a local minimum, okay, this is also going to happen at some x value, right? Let's call it x2, right? The first things first is the fact that dy dx must equal 0, right? So you must have a stationary point, right? And then the second derivative, right, is going to tell you that this is a local minimum if, right, d squared y by dx squared is greater than 0, right? So in other words, if d squared y by dx squared is positive, right, so you can see this mini parabola, right, is smiling, right? So it's positive. That means that at that x value, okay, we have a local minimum, right? So there's actually two types of tests that we are going to use in order to verify that we have a local maximum or a local minimum. The first one is called the first derivative test, and then we also have what I've just shown you now, the second derivative test, right? More often than not, I'm going to use the first derivative test, right? Right, so now let's go back to this question B up here, okay? So we are told that we're given a cubic function, right? And this is the general form of a cubic function, right? We need to show all our workings, right? And determine an expression, okay? So which means that our answer is going to be in terms of these variables that we see in this general form, okay? For the x coordinate at the point of inflection, right? So now I've already told you that in order for us to locate the x coordinate at the point of inflection, right, we have to set the second derivative, so y double prime in this case, because our equation is given to us as y, right? So we need to set the second derivative equal to 0, right? So let's do that, right? So we have our initial equation y, right? We can take y prime, okay? That's going to be equals to 3a times x squared plus 2bx plus c, right? So that's our first derivative function, right? Then y double prime is just a matter of taking the derivative of the first derivative function, right? So we're going to have 6ax, right, plus 2b. Okay, Now, in order for us to find the x coordinates at our point of inflection, we set this equal to 0, right? So 0 is equal to 6ax plus 2b, okay? Right, so we now need to solve this equation for x, right? So we're going to have minus 2b is equals to 6ax, right? So minus 2b divided by 6a, right, is equals to x, right? So the x coordinate at our point of inflection is also given by the expression minus 2b divided by 6a, right? And this is from this general equation, right? And this is quite similar to when we have y is equals to a squared plus bx plus c, right? We know that for this quadratic function, right, the x coordinates at our turning point, right, which is also the equation of our axis of symmetry, remember that that's given by x is equals to minus b over 2a, right? So notice that there's an expression, right, as well for the x coordinate at the point of inflection, right? Okay, so just a quick note, notice that this is from the IEB curriculum, right? So if you're doing the CAPS curriculum, right, you are most probably not going to use this expression, right? Under the CAPS curriculum, what they want you to know is that in order to locate your x coordinate at your point of inflection, right, is that you set d squared y by dx squared equal to 0. Okay.
To